Okay, we're going to get started shortly with the Tyndall History of Global Environmental Change lecture. I'm Philip Mote. I'm president of the Global Environmental Change section, and I'm very pleased to welcome you to the 2019 Tyndall lecture. The Tyndall History of Global Environmental Change lecture recognizes outstanding contributions to our understanding of global environmental change. It honors the life and work of physicist John Tyndall, who confirmed the importance of the greenhouse effect back in the 19th century. It is very fitting that this year's lecturer is Bill Collins. He has an impressive portfolio of interests and contributions to our understanding of the climate system. Using observations and models, he has investigated the spectroscopic properties of CO2 and used surface observations of clear sky radiation over the course of a decade to show the direct effect of increases in atmospheric CO2, extending the work of Tyndall using modern methods to a much richer and deeper understanding of the system and the effects of CO2 and other greenhouse gases on it. And of course, the world in which these observations are made is quite different from what Tyndall experienced and observed himself. Bill is the director of the Climate and Ecosystem Division at Lawrence Berkeley Lab, just across the bay, nestled in the hills. He's also affiliated with UC Berkeley. Before that, he was at the National Center for Atmospheric Research, and it's my great pleasure to introduce Bill, our 2019 Tyndall lecturer.
Thank you so much, Phil, and thank you so much, Julie, for this honor. And I'm very pleased to talk to you about the history of our understanding of the radiative forcing by well-mixed greenhouse gases. This is an appropriate follow-on to the previous lecture because the forcing by these greenhouse gases is what's driving, to the best of our knowledge, the environmental change that we're seeing and is increasingly emerging from the observational record. And I'm going to cover the history and then come to sort of the juicy, controversial bits of what remains to be done toward the end of my talk. I wanted to start, though, by honoring John Tyndall, who is a fellow in the Royal Society. He's a professor at the Royal Institution of London. And he had two major roles in 19th century science. The first was his work on the greenhouse effect and a number of other phenomena, but his work on the greenhouse effect was really seminal. He figured out that water vapor is the most important greenhouse gas in the Earth's atmosphere. He also showed the connection between carbon dioxide and the greenhouse effect. So this was really laying the physical foundations for our modern understanding of the both CO2 as an anthropogenic agent and then water vapor as a very important feedback agent in the climate system. But the other very important role that John Tyndall had was as an educator, and he did a huge amount of work disseminating his findings to the general public, gave hundreds of lectures, and wrote three very influential books, one of which, Heat, I just downloaded from Amazon in preparation for this lecture. So you can still, this book is now 150 years old, and you can still download it from Amazon for a modest fee. So his legacy in terms of educating the public on science lives on. Before I dive into this lecture, I should explain the background to my slides, because it was chosen for a reason. And I'll get there in just a moment, but let me point out that we're just 1 year past the 50th anniversary of this very famous figure of Earth taken from the moon by William Landers during one of the Apollo missions. This is one that did not land on the moon. And the reason I'm showing you this is that we have moved on from taking pictures of the Earth from the moon to taking pictures of Earth from other bodies in the solar system. This is a picture of Earth as seen from Mars, taken by NASA's Curiosity rover in 2014. And now you might be thinking to yourself, great, what's the connection to John Tyndall? John Tyndall is distinctive because he has craters named on both Mars and the moon after him. And this is an image taken of the crater on Mars by a thermal mapping mission, which is also appropriate because Sir Tyndall spent much of his time analyzing the thermal spectrum. So here's the game plan for today's talk. I'm going to start by describing some early calculations of warming, and you'll sort of see these markers on the bottom of the slides track the various topics. I also have a timeline of the papers, and that'll also be tracking which papers I'm discussing. We're going to start in the 1930s and work forward. Then we'll move on to early modeling with general circulation models, circa 1960, 1970. Then the advent of line-by-line modeling of the greenhouse gas spectra, which turns out to be a very important foundation for the work that we're doing currently. An assessment of future forcing by carbon dioxide and other greenhouse gases. This is sort of moving us into the era of the Intergovernmental Panel on Climate Change. A discussion of well-mixed greenhouse gases, and the importance of these was really discovered in the late 70s, early 80s, and is now a very important part of what we do. The chapter I'm leading for the 6th assessment is in fact entirely focused on these agents. And then finally, I'm going to talk about the representation of these forcings in our system models and show you that there's still a lot of work to be done. And I should also say that the contents of my lecture are going to appear in a monograph of a sister agency of AGUs, the American Meteorological Society, which is also celebrating its 100th. And their upcoming meeting in Boston is going to be when they're going to release a monograph with this content as one of the chapters. So I hope if you are interested in this work and other work on radiative forcing, you'll look it up in this forthcoming monograph. Okay, so now diving into the lecture, and you'll have to bear with me. I'm going to show you a lot of beautifully hand-drawn plots, because this is the way that people plotted things back in the 1930s. And I also have to explain some units here. So I'm going to show you a bunch of graphs which show you a quantity of some kind, radiative forcing, absorption, and so forth, as a function of wavelength, which is the way this graph is drawn, or in terms of wave number. So for those of you who are not spectroscopists, this is a measure of the wavelength of light. The bigger the wavelength, the lower the energy of the photons. And the portion of this graph that's covered from 0 to 5 is the solar spectrum. The infrared starts at 5 and goes upward. And what this graph is designed, what I wanted you to show you is that our understanding back in the 1930s of the details of the spectra for these important greenhouse gases, water vapor and carbon dioxide, was remarkably crude. And I'll show you how much better it got once we come into the modern era. But even on the basis of these extremely rudimentary representations of the spectra, it was possible, and this is work by a scientist named Martin, who was at the University of Michigan, to show that as you increased carbon dioxide, the transmission, or what he called deflection, of radiation to space decreased dramatically with increasing concentrations of carbon dioxide. And so this is essentially a manifestation of the fact that as you increase concentrations of carbon dioxide, you increase the greenhouse effect. And what we're focused in now, I just sort of narrowed the range of wavelengths over which we're looking. We're now focused right at the center of the CO2 band, in fact at its peak at approximately 15 micrometers. And the counterpart to this now is modern calculations that I've done and others have done, which show you how the forcing by carbon dioxide changes as you move from levels that we saw prior to, back during paleo times, up to the present day, the pre-industrial concentration of 270 parts per million, up to concentrations that I sincerely hope we don't attain, which are nearly 20 times higher. But this shows you, what this graph is designed to show is how for CO2, the forcing is very, very saturated in the center of the band at 15 micrometers, and so most of the action as you increase carbon dioxide is really in the wings of the band. And everything that you hear from climate skeptics that if you increase CO2, you can't increase the forcing, this kind of calculation puts a lie to. You most definitely can increase it, and we'll come back to our understanding of that in just a moment. So there have been very nice papers by Ray Pierre Humbert summarizing this physics, and Ray pointed out that one of the other complications in understanding the forcing by CO2 is that it's heavily overlain with absorption by water vapor. And the other reason why I want to show you this graph is that this is the other way in which I'm going to plot data. This is in terms of wave numbers, which is proportional to photon energy. So on this scale, the higher the number, the greater the energy of the photon. And so this graph actually covers the infrared all the way up to the edge of the solar spectrum. And what Ray was pointing out in this paper is our modern understanding of how the center of the CO2 band can saturate as you increase concentrations. So the early investigators who were looking at this phenomenon very quickly realized, and in fact this was known all the way back in the late 19th century by Arrhenius, that the forcing by carbon dioxide increases as the logarithm of the concentration. Now, for species that are at much lower concentrations in the Earth's atmosphere, it goes linearly. So this logarithmic dependence is something that's been understood since literally the first calculations of global warming that were done they were done by Arrhenius in 1890. So they're now almost 130 years old. This upper curve, the curve marked A, shows that logarithmic dependence has been baked into our understanding since the very earliest days of our work on CO2. It was baked into calculations at the time. And you could use this relationship between concentration and forcing to build very simple models of the climate system. And the scientists at the time, this is work by Holbert in the 1930s, were building models that look very similar to models that I use in my own classroom. These are models that you could actually write down and solve analytically. What Holbert was doing here was building a box model for the atmosphere, where each layer is governed by fluxes of radiative energy in and out of that box. And he was able to solve these models analytically and go on to show that, in fact, if you doubled carbon dioxide, you could increase the temperature of the climate system by about 4 degrees Kelvin. And that's a remarkably good estimate for someone who is literally building a box model analytically and solving it. And this number, as I'll show you a little bit later in the talk, is within striking distance of the number that we get out of much more detailed global circulation models now that are fully informed by much more modern spectroscopy. So this was an extremely prescient calculation by Holbert. The other thing that he did in this calculation that I won't go through in detail is that he showed that the fact that the atmosphere is in radiative convective equilibrium, that's what the acronym RCE stands for, is critical for understanding the temperature response of the climate system to increased carbon dioxide. And we'll come back to this point a little bit later when I get to this seminal calculations done by Suki Manabe in the 1960s and 1970s. One of the other, one of the other calculations that was done at this time is to understand the effects of carbon dioxide on the emission of thermal radiation to space. This is work by Guy Callender in the 1940s. And what Guy showed was that there are, and again, I'm now plotting this in terms of wavelength. The center of the CO2 band is about at 15. 5 on this axis is the boundary between infrared and the solar spectrum. And what Guy showed in this hatching is that there are portions of the infrared spectrum where the absorption is so strong that you'd expect the emission to space to drop dramatically. And again, in this modern paper by Rapier-Humbert, published in 2011, we've now been able to verify this effect. So this graph on the left shows a model calculation in blue and direct measurements from a spectrometer flown by NASA in red. And the depression in the emission to space due to carbon dioxide that was predicted by Guy Callender is shown there very nicely at a wave number of about 600 to 800 wave numbers in these units. So in other words, carbon dioxide makes the planet look very cold at those wavelengths. And the scientists back in the 1940s were able to predict that effect. The first, and I'm almost done with sort of this very early period, and we'll move into the more modern period here in just a moment. I want to end with a scientist named Gilbert Plass, who did some really phenomenal calculations in the mid-1950s using some of the first digital computers that were coming online at the time. He was able to go back and revisit that box model of Plass and now reproduce the transfer of fluxes through the Earth's atmosphere with a computer calculation, and showed again that if you doubled carbon dioxide, you would essentially increase the temperature of the Earth's climate system by somewhere between 3.5 and 4 degrees Kelvin. He also showed with this model that you would cool the troposphere. And this turns out to be this dipole signal warming the troposphere, cool the stratosphere. This dipole signal cooling the stratosphere, warming the troposphere is a striking and unique signature to greenhouse gases that we've used for attribution of climate change. And again, I'll come back to the work that Suki Manabe did to prove this in a computer model in just a few slides. Gilbert also looked at did some work on anticipating the effects of CO2 on sea level rise, which I won't have time to describe. Let me move now on to the slightly more modern era, where 10 years later, Suki Manabe at the Geophysical Fluid Dynamics Laboratory at Princeton was starting to build the first simple models of radiative convective equilibrium. And this is the first calculation that he published in the mid-1960s, where he was able to show, this is the temperature response throughout the entire troposphere to increasing carbon dioxide. He was able to show, in fact, that you get this decrease in temperature in the stratosphere, increase in the troposphere, and noted again that you'd be seeing temperature increases at the surface of around 3 to 4 degrees Kelvin. He then went on in the mid-1970s with a much faster computer to create a general circulation model of radiative convective equilibrium. So we can now look not only at a column, but at the gradients between the equator and the pole. This is a graph where he shows that in the stratosphere, that's what the hatching is indicating, stratosphere will cool, troposphere will warm. And this is informed, for example, literally all the work on detection and attribution of climate change that's been done since Ben Sander did some of the similar calculations back during the second assessment report for the IPCC. So this is a clear signal of greenhouse gases. You do not get this dipole signal, for example, from changing solar luminosity. You do not get it from volcanic aerosols. You don't get it from aerosols. This is a real, literally a fingerprint of increased greenhouse gases in the atmosphere. And the fact that we can see this in observations is one of the reasons why we're so confident that greenhouse gases, well-mixed greenhouse gases, are the cause of global warming. This single paper, though, was seminal in a lot of other ways because it anticipates so many of the signals that we see in modern models. Suki pointed out you'd see polar amplification, and the signal for this, although it's somewhat hard to tell from this graph, is the fact that these two lines separate more and more as you get up to high latitudes, 80 to 90 degrees, means that the poles are warming when you increase carbon dioxide much more than the equator. And so he was able to show polar amplification, a well-known signal, and one that we observe now, even with this incredibly crude model of the climate system. He was also able to demonstrate the response to the hydrological cycle. And I'll just tell you the headline messages from this graph, so that he showed that the storm tracks will shift northward, which again is a remarkable accomplishment. And he also showed that the response of evaporation over the Earth's surface would be remarkably constant equator to pole. This is something that Brian Soden was talking about on Monday, and these signals that we see in modern climate models were anticipated by Suki Manabe literally 40 years ago now. So remarkable accomplishment from a very simple climate model. And he also dove into looking at snow feedbacks, showed that we'd anticipate strong feedbacks from the meltback of snow thanks to the increased warming from carbon dioxide. Ramanathan, who was also at this point launching his work on climate modeling at NCAR. This is a picture of Ram from that time, a much younger Ramanathan. He also showed the polar amplification signal and went on to explain that there was a large seasonal cycle at high latitudes. So this is you get a very large seasonal cycle in the warming at 80 degrees north, which you do not see at the equator. And so this is the work that Ram did to sort of build on that foundation that Suki laid roughly at the same time. So these two groups were getting going on building detailed models of the climate system at roughly the same time and looking at the effect of CO2. So I want to switch gears here now slightly and talk about a tool that is critical to our understanding to be able to connect these climate signals back to basic physics that we can measure in a laboratory. And that connection is made through something known as a line-by-line model. Line-by-line models literally look at the tens of thousands of transitions, quantum transitions that we've cataloged for water vapor and carbon dioxide, calculate the effect of each of those on the spectrum, and then compute their effects on the fluxes in the Earth's atmosphere. And it's this way that we can tie the physics that we measure in the laboratory to measurements from balloons, from, say, the DOE ARM program, and also use these models to inform how we build parameterizations of radiative processes in climate models. So I need to take a brief detour here to explain the history behind these models because it's critical. I use them routinely in my own work, and so they've really underlaid our ability to know that we're getting the right answer for the right reason. These models weren't possible with early computers. They only became possible really roughly 50 years ago with the advent of machines in the 60s that were fast enough to do detailed treatments of the spectrum. This is one of the first line-by-line models done by Roland Drayson, in which he calculated the effects of CO2 and increasing CO2 on the transmission through the Earth's atmosphere at that time an unheard of resolution of 1/1000th of an inverse centimeter in wave numbers. This is really a pioneering calculation. And then this was turned into sort of a community code known as fast code. This is a sample calculation of the transmission through the 4.7 micron band of CO2 done by Henry Smith, this time in the late 1970s. And these models would then go on, we went on to use these models to test them against balloon measurements. So we knew that these line-by-line models were working correctly because we could compare them directly against detailed calculations of the emission of the Earth's atmosphere. And the other way in which they became particularly useful is that we could use them to test GCM codes. So I mentioned early on that these line-by-line codes sort of sit in the middle between detailed spectral measurements of the climate system and our translation of that knowledge into GCMs. So I've just illustrated that sort of critical handshake mode in the space of 2 slides. This is work by Fels and al. At GFDL, in which line-by-line models, almost for the first time, were used to test the radiative cooling rates, in this case in the infrared, of the GFDL climate code at the time. And you can see the remarkably good agreement between the model parameterization, which is the jagged line, and the line-by-line calculation shown in black. So really quite a testament to our ability to capture this physics, even in climate models that are now almost 30 years old. The knowledge behind this, the underpinnings for this are line-by-line, these catalogs that are made of the spectroscopic data that we're getting out of the laboratory. And there are 2 of these really, one known as HYTRAN, that's maintained by the Harvard-Smithsonian Institute. And this is the first generation of HYTRAN from the early 1970s. Fast forward to today, and it's still being developed. This is the most recent version of HYTRAN from 2016. This is showing that we're still adding lines to this database. This is the lines that are being added for methane. And I published a paper recently where I showed the history of the additions of lines of methane to the database. So we've now increased them by nearly a factor of 30. We're marching toward the solar spectrum. But as I point out in this paper, we still have a long way to go. And so there's still a lot of work for spectroscopists to do. This is the counterpart in Europe, known as the Giza database. And again, the colors on this graph indicate the contributions being made for each edition of these databases through the hard work of spectroscopists and being captured in these databases and used by the broader community. Where does this lead us? And this is the last thing I'll say about line-by-line models. Marty Malenczak and several of us published a paper recently in response to some work that had been trying to cast doubt on our knowledge of CO2 forcing. And we point out that based on our current catalogs of line spectroscopy, as far as we can tell, with line-by-line models, the remaining uncertainty is less than 1% in our ability to calculate the response of the Earth's radiative energy budget to increasing CO2. So this is how far we've come since the dawn of line-by-line modeling, and in fact, since that very crude spectrum that I showed you as the very first slide in my talk. We're now at the point where the remaining uncertainty in line-by-line models is less than 1%. What I'm going to come back to at the very end of my talk is to point out that unfortunately, this high level of uncertainty in line-by-line models has not yet made its way into our models of the climate system. So that's the reason why there's a lot of work to be done, especially by early investigators in the field. All right, I'm going to jump ahead before I come back to assessment to other warming greenhouse gases in the climate system. So I've only been talking about CO2 so far primarily, and I just mentioned methane. That's a segue into the fact that by the late 1970s, early 1980s, climate scientists had recognized that there are other gases in the climate system, warm-mix gases, that can have an appreciable effect on the Earth's energy budget. And this is an early paper by Ramanathan where they were starting to construct chemistry climate codes. And here he's looking at the pathways going from emissions through chemical transformations to concentrations of these gases. And you'll notice in the middle part of this figure, the concentrations of methane and nitrous oxide with the second and third most important anthropogenic greenhouse gases, along with some other compounds I'll come back to in just a moment. So this is a very important era where we recognize that CO2 is not the end of the story. And in fact, Ram wrote a very important paper with an advanced study program postdoc named Leo Donner, who's now at GFDL, back in 1980, where they looked at the effects of increasing methane and nitrous oxide on the fluxes, radiative fluxes in the Earth's atmosphere, and showed that these effects are very large, that you must account for them if you're going to properly treat climate change. Jim Hansen, at the same time, was looking at the effects of these gases on depressing the emission of Earth's radiation to space. And this paper that was published back in 1976, it took a very long time to observe these effects. But John Harries published a beautiful paper in 2000. I'm sorry I don't have the citation on here, in Nature. And this paper has gone remarkably underappreciated. This is literally the first time we had demonstrated that greenhouse gases are affecting the spectral radiation in the Earth's atmosphere. What he did is he took two satellites that flew 40 years apart. One of them was one of the early TIROS satellites. It's featured in Michael Crichton's movie, The Andromeda Strain. The movie ends with early crude footage being taken from this very satellite, and contrasted it with a satellite flown in just around 2000, differenced the spectra between the two, and showed in the upper graph how the spectrum had changed between these measurements nearly 30 years apart, and compared it to a model calculation in the lower part of the figure, and showed that the spectral features that are observed line up beautifully with what you would predict how the spectrum should have changed thanks to increases in methane and other greenhouse gases in the period between those, when those two satellites made measurements. And this is literally the first smoking gun that I'm aware of where we had shown the effect of increasing greenhouse gases on the emission of Earth to space. It's a remarkable paper and was anticipated by this early work from the 1980s by the pioneers like Jim Hansen and others. Jeff Keel invented the term known as the dirty window, and this is actually, I learned about this from Ram when I joined him as a postdoc. I was getting one of my very first lectures from him about understanding radiative transfer. He brought up this idea that we're smudging the window. The mid-infrared is literally the way that the planet ventilates heat to space. It's the window through which the planet manages to dump heat back to space that it's absorbed from the sun. If you block that window by making it dirtier, you will make the planet hotter. And Ram and others, Jeff Keel, were busy figuring this out in the mid-1980s. You'll notice on this graph, so this is a plot of the dirty window, again as a function of wave number, which is proportional to energy. Methane and nitrous oxide are sort of listed low in this figure, and then there are a whole bunch of other compounds we've not talked about just yet. I'm about to come to those. These are the compounds governed by the Montreal Protocol. So what happened is that in the 1970s, this remarkable refrigerant, pair of refrigerants known as CFC11 and 12 have been invented actually by the same man who invented leaded gasoline. So he really deserves a statue as sort of a double climate criminal. I won't mention his name because of the way I just described him, but he invented both. And this is a great replacement for ammonia in refrigerators, right? So you don't want ammonia in your kitchen, you want CFC11 and 12. These were detected in the Earth's atmosphere in the 1970s by Lovelock. And so Lovelock made his pioneering measurement, and in the same paper, unfortunately, he made a statement that I think he's come to regret, which is the presence of these compounds constitutes no conceivable threat. Doubly wrong on that score. These compounds, as you know, deplete ozone, and this is the reason why Paul Crutzen and several others got the Nobel Prize in the 1990s, and Susan Solomon has a statue to her, a wax figurine in the Smithsonian, and has features named in Antarctica after because they figured out that these compounds deplete ozone. They also have a whopping big effect on the Earth's radiation budget. This is the seminal paper by Ram where he showed that trivial increases in the concentrations of these compounds would have a gigantic effect on global warming. And so this is now we raise two alarm bells around these compounds. They deplete ozone, they cause massive global warming. And this is a paper that Ram wrote right the same year as the advent of the Montreal Protocol, which was only designed to constrain their effects on the ozone hole. It was really not designed because they have a big impact on the greenhouse effect. But Ram noted that just a 1 part per billion increase, this is 1,000 times smaller than the concentrations we're talking about for carbon dioxide, that would have huge, appreciable impacts on the temperature of the Earth's surface, compound by compound. So if you add up, most of this graph is dominated by incredibly tiny, minute trace constituents in the Earth's atmosphere, each contributing a tenth of a degree. Add that all up and you've got a fairly large temperature signal. And this graph makes the same point, as does this figure by another paper by Rahm at around the same time, where he's contrasting the warming from CO2 only, which is shown in dashed line, with what happens if you add in methane, nitrous oxide, all these chlorofluorocarbons in the F species that are now regulated by the Montreal Protocol, and it really adds significantly to global warming. And Jim Hansen was also making roughly the same point at the same time. This looks a lot like the IPCC bar graphs with which we're all very familiar, but this is actually in a temperature scale enumerated by species. And again, this is showing, this was done in the early 1980s. You'll notice that at the right end of this graph, he's got the CFC at 11 and 12 having the same forcing impact on the climate system as methane and nitrous oxide. So thankfully, the Montreal Protocol has sort of reversed this thinking that scientists had at the time based on the rapid rise of those compounds in the Earth's atmosphere. So now I'm going to switch gears to the assessment of all this understanding that really began to emerge in the IPCC assessments at the time. So I'm showing you two of them. This is work by Keith Shine done in the first assessment report of the FAR. And the joke that I like to make about the IPCC is that it's in the job of making predictions, but they could have predicted that the word first and fourth also begin with the letter F. So by the time we got up to tar, they clued into this, and that's when we went from using letters at the front of these assessments to using numbers at the end. So we went from FAR, SAR, TAR to AR4. So Keith did this graph for the FAR, and Rahm did this parallel figure for the third assessment report. You know, these are based on highly simplified, highly parameterized formula that are based on the line-by-line models and the GCMs that I described earlier. So these formulae are now playing a critical role in our ability to compute things like, for example, the global warming potential, the global temperature potential, and hand this information off to policymakers. These sort of graphs are what appear in the summary for policymakers for IPCC. So these represent sort of a grand condensation of the understanding that's been developed over really since Arrhenius, 1 century before 1990, did the first global warming calculation. 1 century later, we're now able to condense that information and hand it off to policymakers. And in fact, the very first summary for policymakers was done in conjunction with the first assessment report. And this is another figure that Keith showed, now summarizing the evolution of this forcing as a function of time. Okay, so I'm now coming to really the last part of my talk, the last two parts. First, where we stand with respect to reproducing all this understanding in our system models, which is makes me a little depressed, I have to admit. And then where do we go from here? So this is a paper done by Bob Suss in conjunction with the first assessment report, where he took Earth system, and GCMs at the time, these were uncoupled atmosphere-only models, and computed their response to doubling carbon dioxide. And given the fact that I've told you that we can do this in line-by-line models to less than 1% error, you'd think that we'd see 1% error in GCMs. Lo and behold, you don't. You see sort of a range that's 34% end-to-end, so nearly 1.5 decades larger than the uncertainty in line-by-line models. So that sort of told us that we needed to do some work. I did a study for the third assessment report the fourth assessment report led by Susan Solomon. And what I'm showing here is the comparison between line-by-line models in blue, which have very narrow error bars. That's the reason why there's a cross and essentially no error bar that's visible. And then the forcing by CO2 that's shown as a box and whisker diagram. And you can see that those box and whisker diagrams get pretty fat, especially for the shortwave component compared to line by line. So again, this was illustrating to us that we need to do a lot of work still. So this is for the fourth assessment report. Here we are on the 5th. Here's some papers by Brian Soden, illustrating that again at the top and also at the surface, we still have an appreciable spread. And so, you know, I've been starting to compare myself to King Lear, pardon me, ranting on the heath, and I don't like to rant. Fortunately, Brian Soden decided to step into my shoes and rant a little bit in partnership with Jan Feldman and myself. We published a paper last year where we compared our progress from 1993 up to 2015. And what this graph shows is that the GCM community has really stopped making radical improvements in the accuracy of its radiative parameterizations. So where do we go from here? Well, we have built a framework to assess this in the ongoing 6th assessment and 6th couple model under comparison project, known as the radiative forcing model under comparison. This is being led by Robert Pincus, Piers Forster, and Bjorn Stevens on the infrared side, and by a team of us on the shortwave side. We're using line-by-line models to confront GCMs, and we're now getting submissions, and Robert just kindly sent me the first paper, which shows how well the line-by-line models are performing. In the interest of time, I'm going to skip this and essentially say that we're now repeating this exercise for the 6th assessment. But I now want to do a little bit of a look toward the future and say, where do we go from here? I think the future is pretty bright for this field for 3 reasons, and I want to come back to what has been the traditional 3-legged stool of climate change, namely theory, computation, and observation. Some would argue that there now needs to be a 4th leg to this stool, so it's even more stable, which is machine learning. And I'd be happy to talk about that during our Q&A session, but I'm going to, for the time being, rely just on the 3 legs of the traditional stool. One of the things that has enabled much of what I've shown you and is now enabling us to literally, for the very first time, use line-by-line models and to analyze the globe in its entirety and to confront GCM parameterizations on timescales of at least days to weeks against line-by-line models is the remarkable increase in computing power. So I'm going to show you 2 graphs. This is the graph for GFDL. And what's happened since GFDL got into this business is that computing has increased, their ability to compute has increased by 10 billion-fold. And this graph starts back before I was born. The very first computer on here predates the invention of Fortran, which I'm also happy to say is slightly older than I am. So, and it's still being used to my remarkable shock and shame to build climate models. But there you have it, 10 billion-fold increase in computing power. And this is enabling us to do some remarkable things now in terms of examining radiative processes. I got the exact same graph from NCAR, and sure enough, it also reveals a 10 billion-fold increase in computing power, largely because we're locked into the same vendor set. So, but this has enabled a lot of work for us. I'm going to need to use, I think I do have control of the mouse. Phil very kindly mentioned that we can also observe these phenomena in the climate system in more detail than we've been able to do before. This is the first, those results that Phil was alluding to, a paper that we published 4 years ago, a paper led by my colleague Dan Feldman and I, and based on a concept that I came up when I first joined Berkeley Lab back in 2008. So this paper was really, it took us nearly a decade to execute this idea that I came up with shortly after I moved from NCAR to Berkeley Laboratory. What this graph is going to show is the connection between carbon dioxide and the radiative forcing by it. Let me see if I can get this movie to play. Phil, I may, let's see, could you click, if I may entrain you, because I don't have my reading, well, yeah, could you click on that graph and get it to do something? Okay, interesting. Oh, maybe, you know what?
They're 2 mice.
There are 2 mice. One of them is just a placebo mouse. This is the real mouse. Okay, so there you have it. There's CO2 increasing. There's the radiative forcing increasing. This is from the Southern Great Plains. And this is from the parallel site that's maintained by the Department of Energy at the North Slope of Alaska. Notice how beautifully they track each other. And the two things I want to point out to you that you can see a rising trend, which agrees very nicely with models. It also agrees beautifully with line-by-line models and with one of the parameterizations that we're using, GCMs. So we've got, this is what we would have predicted, this increase, based on rising concentrations. The other thing you'll notice is a sawtooth pattern, which is due to this annual cycle in photosynthesis and respiration by plants. This was noted by Keeling when he first made detailed observations back in the 1950s from his observatory in Hawaii. This is the first time that this natural breathing, the radiative signature of this natural breathing in the climate system had been quantified. And the last thing, just to make a slightly political point, is that this was measured 50 miles or so from the home of the first EPA administrator in this administration, who was asking for evidence of the connection between the two. So I would argue that here's the evidence, and it's a very pleasant drive from his home, the Southern Great Plains site of the Department of Energy. We also did measurements from the site of the effect of methane. And this is a figure that we published in a paper last year, showing that the forcing by methane was tracking the hiatus that we observed in the early 2000s in methane concentration. So methane remained flat. Sure enough, the forcing remained flat. When the methane began to increase, the forcing began to increase. This break in the curve was something that we asked a computer to figure out if we needed it. And sure enough, the computer said, yes, you do need that. That break is highly statistically significant. And it located it correctly at the point when the methane began to increase. So that this curve was introduced by a statistical model that was asked to falsify the hypothesis that there was a break in the time series. Sure enough, there is a break in the time series, and it's associated with this rapid rise in methane in the Earth's atmosphere starting with 2007. Almost done here. I'll end with the fact that I'm working now on theory to improve the model. So I'll just end by saying that I've now built what I believe is the first principles. Pardon me, I'll need to go back. Oh, I've just ended my lecture effectively. Let's see if I can go back. See, there we, nope, it's going to, there we go. I built a theory for how to treat Beer's law in gray media, which I'm happy to describe to you during Q&A. And I'm now preparing to test this as part of an upcoming intercomparison of the GCM parameterizations. But I wanted to end by just saying, noting by how far we've come. So this is Tyndall's apparatus that he built for measuring the greenhouse effect. And we're now at the point where we can look at the spectrum in great detail, both in the astronomical and terrestrial applications. Use this for remote sensing. And I wanted to end with a few final words from John Tyndall before I turn it over to Q&A. From experiment and observation, drive theory, and ultimately computation as well in the modern era. So that, he was very prescient about noting the connection between those two. It's really important to recognize that the knowledge that you gain really doesn't stay contained, and in the field in which you discover it, it leaks out. And I've pointed out how much work in one field of radiative transfer has permeated our knowledge of the entire climate system. And words to end by that, again, harken back to the previous lecture. It is as fatal as it is cowardly to blink facts because they are not to our taste. So with that, let me close and take any questions you might have. Thank you very much indeed.
So there are microphones in the aisles if you want to ask a question. While that's happening, Bill, you've worked both with these line-by-line models and with GCMs. What do you, and you mentioned sort of in passing machine learning, where do you see the future of the radiative portion of climate models, and also looking back over the past as we went from the fairly simple radiative convective equilibrium?
So the future of, we're about to enter, one thing that's about to happen to us is that we have built all these parameterizations assuming that the atmosphere is described by, for radiative transfer, it's described by one coordinate, which is the vertical. And we're about to enter an era where photons, we'll have to treat the lateral transport of photons. So that's because when we start building cloud resolving models, the photon diffusion path length in the Earth's atmosphere is 60 kilometers. That's over the horizon. And some of those effects, some of those edge effects, as people in this audience have worked on, are not negligible. So we're going to have to rebuild those parameterizations to treat three-dimensional radiative transfer, at least think about how to parameterize it, and embrace that as part of the work that we do. So that's going to be a major revision that's coming up soonish. There's been a lot of discussion about replacing them with machine learning, and those experiments have been around since the 1990s. I was just talking to a colleague over lunch, and he said that the reason they've never been adopted is that numerical weather prediction groups are very leery of having rude surprises tossed at them. And the problem they have is that if you have a neural net and it does something rude to your calculation because you just hit an edge case, it's really hard to figure out how to diagnose it and also, even worse, how to fix it. So that's the reason why the NWP centers, despite the enormous speed up from adopting neural nets, have never adopted them. They're still using conventional radiative parameterizations. So, that's this is one of the reasons why I'm kind of keen to get them up to the standards of line-by-line models. I see my colleague Phil Rash has a question for me.
Phil Rash.
Yes.
Yeah, thanks, Bill. I'm sorry I didn't listen to Phil's question carefully enough to make sure I'm not repeating anything. But I'll just ask if knowing what the differences are between the line-by-line and the current, or let's say the previous generation, the AR5 generation of radiative transfers, can you give us a preview or anticipate what kind of implications there might be for either climate change problems or the operation of climate models if we do the calculation accurately rather than the way we have been doing it?
Thank you so much for that question, because that was a point I meant to make. So, as everybody knows, and a number of people, again, in this audience have worked extensively on this, the response, which is delta T, is equal to climate sensitivity, lambda times delta F. And if you have uncertainties in the forcing, those slosh onto the response that you're trying to measure. The error that we have in climate models now is large enough to alias onto the differences between scenarios. So all this work and all this effort that the climate community is spending on looking at this Baskin-Robbins sort of assemblage of different scenarios with slightly different concentrations of radiative forcing agents is actually being washed out by the errors in the radiative forcing. In essence, what's happening is that rather than having 50 climate models look at one scenario with essentially one prescription for climate forcing, you have 50 climate models with 50 different descriptions of the radiative forcing. And that's big enough to alias onto the very signal that we're trying to explain to policymakers, which is if you reduce emissions, you will see a benefit. This error is aliasing onto that core message. So I think we need to get rid of that aliasing. So I think that would be a major benefit for the societal impact of these models if we got rid of that. Because otherwise we're expending a huge amount of computer time on sort of generating an unwanted source of uncertainty.
John Nielsen-Gowan.
How much of the model spread in radiative forcing is associated with the radiation code, and how much is associated with differences in depiction of clouds within the models?
Almost all of it's associated with the code. I didn't have time to talk about it, but there have been a pair of papers, one published by my group and another by Lawrence Livermore, that showed that the uncertainties in the shortwave, which we haven't talked about in this lecture, but in the absorption by water vapor in the shortwave, have a big impact on the hydrological cycle. So remember I talked about the radiative convective equilibrium and the fact that water is coupled into that. If you get the water vapor the effects of water vapor on the shortwave wrong, you will alias onto the response of the hydrological cycle to global warming in a fairly major way. And we showed that aliasing is connected with errors in the radiative parameterizations. So something as fundamental as how water supplies will change in the future, again, is being affected by these errors. Coming back to Phil Rash's question earlier. Eric.
Great talk. One of the things that people always talk about in the climate model context is just how expensive radiation is.
And
it's so expensive that you only do it every 20th time step or every hour or some such thing. What do you think are the sort of bad, sort of unintended consequences of doing it that way? Not doing it every time step?
Well, the groups that are doing it have actually, what they've done is they've backed it off to a hair's breadth that's trying to really impact their climate simulation. So they're, NCAR, for example, when they backed off the long wave calculation to every 12 hours, they studied how far they could, how infrequently they could do it before they started to see appreciable signals in the climate system. NWP groups have done exactly the same. So, I mean, I applaud groups for, they're essentially asking what's necessary and sufficient for us to have a reasonable climate simulation. And they're sort of trying to answer the question, what's sufficient? And so I'm happy that they've done that, and they've done it in a careful way. Tom Ackerman,
Bill, thank you for a very entertaining trip down memory lane for many of us.
Good.
I was struck by your comments about John Harry's paper and also the recent work that you've done. And I find these very compelling evidences of the climate change problem that we face. But I also find them very difficult to use in audiences that are not radiatively transfer educated. And I don't know if you have any thoughts about that. To me, it is the smoking gun. To you, it's the smoking gun. But how do I convince the rest of the world that it's a smoking gun when they don't understand what a photon is?
Yeah, that's a good question. I just showed that graph to a ladies' luncheon in Nashville. I didn't pull them afterwards to see how well that graph went over, Tom. So it is a challenge. Since you asked the question, this gives me a chance to segue to a violently different way of communicating, and it's in the spirit of John Tyndall. So I have, because of the difficulty of relating climate change as a physics problem, I've now gotten into the business of being an entertainer. So for those of you who are interested in looking at my alternate life, Google Climate Music Project. When you leave this lecture, we are now we are touring now with performances that are composed against IPCC simulations. And we have found that is a far more effective way of communicating the science to audiences. We accompany it with these graphs, but they can hear it musically, they can see it visually, and the response of people to the graphs when they're accompanied by music is remarkably different from when they're not. So this is my sort of segue into my John Tyndall-esque efforts to communicate the climate science more effectively.
Eric has a follow-up.
Uh-oh.
No, I don't have a follow-up, but the business of entertainment reminded me that when I was a kid, there were really great sci-fi movies about Venus and how it was inhabited by various sorts of dinosaurs and ferns, and it rained a lot there, and it was muggy. And now we find that actually it's a lifeless planet with a 400 Fahrenheit surface temperature.
Yeah.
That whole history of understanding global warming in a sort of this astronomical sense, that kind of maps onto the same period as your timeline for understanding radiative transfer on Earth. And I'm just wondering, do you know anything about that? Was there a sort of cross-pollination between people that were working on the terrestrial problem and people that were looking at Venus and Mars and so on?
The Earth's atmosphere system is a lot easier to study because it's not so optically thick. So I was working at Arecibo as an undergraduate when they were using radar to penetrate the atmosphere and begin profiling what was underneath, and of course some of the probes that went down. I would say that in the context of radiative transfer, one of the major cross-pollinations that occurred from astronomy to terrestrial work was a method for solving the radiative transfer equation and embracing the full complexity of the spectrum that was first developed by the astronomical community and then borrowed starting in the late 1970s and really in the 1990s, known as the correlated K method. That arose in the astronomy community. Now we have returned the favor because the astronomers are now using methods for dealing with inhomogeneous radiative transfer and complex media that were developed in the atmospheric community. So that transfer does go both ways. But that's a great question, Eric, and I'd have to look it up to understand how much crosstalk there was between comparing different atmospheres with very different greenhouse effects and understanding the Earth's. Probably the right person to ask that question to is Andy Ingersoll. So,
one last question.
Okay. Very good talk there, Bill. What do you think of the spectral fingerprinting that Clario wants to do? Will that add a lot of value to coming up with more precise measurements of the greenhouse gases as time progresses? You see a lot of value in that?
Thank you. So the question concerns a mission known as Clario, which is designed to put an absolutely calibrated radiometer in space, and each part of the optical train will be traceable to not one but two separate NIST traceable standards, so fundamental mass, length, and time. And so it's really designed to provide the first absolutely calibrated measurement of the Earth's emission to space, and prototypes of that are being developed in the shortwave. The beauty of this is that in principle you could fly, if you had two of these instruments flying 20 years apart, with two different measurements, you could draw a straight line through it and know that the slope of that line is accurate. And you cannot do that, unfortunately, with most operational instruments, even research instruments now. So getting to the point where we have a climate accurate record is another grand challenge going forward, and it's another great point to end on. It's a future challenge, and we're going to start doing this in the shortwave now with an instrument on board the space station, which is designed to intercalibrate literally every passive solar scanner in orbit now, and to put them all onto the same footing. So we can do the same thing with the infrared, and that's a very, very important step forward for building an accurate, usable climate record of how things will change, not on year-to-year timescales, but on decadal timescales. Thank you for asking that question.
Thank you very much, Bill, for
Thank
a
you.
fascinating talk. Appreciate it. So that's our Tyndall lecture. Head over to Moscone North for the Union Honors and Awards.